Hi everyone. Okay, so today I will introduce the Bellman Optimality Equation and the Q function. So let's say we already have an optimal policy. I have already talked about optimal policies in a previous video, and we ask what happens when acting greedily on the optimal value function no longer improves it. It means that we have found the optimal solution, and the value function that satisfies this condition is the Bellman Optimality Equation. So mathematically it is V star for a state also let me use of max for possible actions of okay, let's say next state based on some probability, expectation, reward signal plus gamma, this is not y, of V star of the next state. Okay, so let's see if you get a good you have gotten a good value function. All you have to do is check both the right hand side and the left hand side if they are equal. And once we get a V star, we can find a corresponding pi star. I mean, once we find the optimal value function, the optimal policy is the one that greedily selects the best action from each state. So pi star, corresponding pi star is argmax expectation, the next state based on some probability, okay, I've already included expectation of reward signal, gamma, V star of the next state. Okay, now by the way, I think I should talk about this expectation here again, because that is important, at least for stochastic environment. I mean, used, for example, you know that it is used when the environment is stochastic, meaning that the same action can lead to multiple possible next states, each with a certain probability. For example, going right from a state might take it right 70% of the time and maybe up 30% of the time. By the way, this is the system that we are going to be using. In the upcoming videos, I plan to introduce even more realistic systems. Now, looking at this expectation, the reward signal, the next state based on some probability, I mean, it shows you that to compute the policy, you need the full dynamics of the environment. For example, the raw signal and the transition probability matrix. Now, what if we ask, what if we had a function whose policy doesn't need to know the rewards and the transition probabilities, and that is where the Q function becomes useful, and that is where we use the Q function. Q function. Okay. Now, in here, for example, let's go back to this. Instead of asking how good it is to be in a state, why not ask how good it is to take a particular action from a particular state? So the Q function is something like this, which takes in not only the state but also an action. There's still an expectation, reward signal plus gamma of the Q function based on some policy of the next state, and the next action of the next state based on some probability. Yep. Okay, you see that they are they are actually very similar. So really only the difference here is that between the V and the Q is that the Q more like takes in both the state and actions, but while just this takes the state. Now if we already have the optimal Q values, let's say we find Q star. By the way, related to this is the general Q function. We can also find a Q star. We can get an optimal policy, which is something like this. I don't want to go into in detail of how the policy gotten from the Q function, but it is something like this. Argmax of A, Q star, if we manage to find it, of the next state, of a state and action. Don't worry, I will introduce an example here. So notice that the policy here is actually simple. This is argmax, so not argbound. There is no expectation, no probability matrix. All we have to do in here is just pick the action with the highest Q value. Okay, I think at least let's do some example, because this can become complex. We are going to be using this system. So let's compute, for example, state 5, Q of 5 action right. And I will be, for this example, I will be using a stochastic environment just to make it a bit more realistic. So let's say before then compute it here, let's say gamma will be 0.9, reward signal for any action is minus 0.1 for simplicity, and the probability system for the stochastic environment is going to be 0.8 for intended state, 0.1 opposite direction. So for example here, if the agent from 5 decides to go to state 6, the intention is state 6, and that will be, it will have a probability of 0.8, and state 1 and state 9 opposite directions are 0.1, 0.1. The summation is 1. Okay, so we have a stochastic environment. Now I want to more like tell you that when computing the Q of a state and action, we have this policy here. We don't need to define an initial, for example, deterministic policy that always tells it go right, go right, go right in any state. When we use the equation to learn, we often start with random Q values, and the policy emerges over time as we update the Q, our Q function. All right. So from the equation, we can take in the expectation inside. Here we need the raw signal, which is minus 0.1 plus the gamma of 0.1 times the expectation. Let's see, I'm going to call it expectation value. Let's compute the expectation, because that is where most of the more like information comes in. While we have a stochastic system, the intention is go right. So right is 0.8 times the, when it wants to go right, it will end up in state 6. So, and in state 6, you ask, what is the current best Q value at state 6? All you have to, because in state 6 there could be Q value for 6 right, 6 up, 6 left, 6 down. So what is the current maximum Q value for all of those states? And let's say it is 0.7. Opposite directions of 1, the probability is 0.1 times you ask in state 1, what is the current best Q value of state 1? Let's say it is 0.5. Then 9, probability 0.9, you ask in state 9, what is the current best Q value of state 9? Let's say 0.4. By the way, I'm just making up these numbers. Initially, when in programming, you initialize these Q values and you update them with time. By the way, for all these equations and this, there's going to be a Jupyter notebook that you can play with to really understand this information further. All right, so this is 0.65, and when you plug 0.65 here, you will end up with 0.485. Okay, so far so good. Now once we have Q values, let's say for state 5 up, down, left, state 6 up, down, left, for all the state up, down, left, even if they are not optimal, we can extract a policy by choosing the action with the highest Q value at each state. So let me show you this. So for example, state 5, maybe Q of state 5 up is 0.32. Q of state 5 right, we have already computed that value, 0.485. Q of state 5 down, 0.4. Q of state 5 left, 0.1. So you just ask, what is the maximum? The maximum is this. We don't need this. All right, we don't need them. All we need is the Q because it is the maximum. So we can see that this is the policy. The policy of state 5 is going to be right. Okay, so yes, let me, maybe 5 going to be right. Okay, now there's also one more thing. Let's go back to this. The complexity, more like the space complexity of the value function is based on the number of states. So the space complexity is S. But in here, for each state, we need the information for all the possible actions. So it is S by A. All right, so far so good. I hope this is clear. Please let me know in the comments if you have any question. And there's going to be a Jupyter notebook for all this Bellman Optimality Equation for this that you can, it's really simple, that you can check in to further understand this. Thank you for watching. Bye bye.